Okay, let me explain. Darth Vader and R2-D2. I'm R2-D2. My friend was Darth Vader. This was 1977 when the very first Star Wars came out, and it was spectacular. Nobody has ever seen any movie like that before. So that's how I'm going to start out this part 2. So this is nuclear chemistry part 2. And before we go over the uranium disintegration series, which is very cool, and artificial transmutation, we have to talk about the history of radioactivity. Now, Henri Becquerel, he was a French scientist. And in 1896, he was doing some pretty cool stuff. Here was his deal. He had a photographic plate. And in those days, and in the days of cameras that had film, you couldn't expose the film to any light because it would expose the photographic plate. All right, it would turn it all black. So what he was trying to do is he was trying to show that if you put a certain material, and he was using some type of uranium rocks, he thought that if you put the uranium rock in the sun would energize this uranium rock, and the uranium rock would give off rays. So what he was trying to do was he got a big glass photographic plate, and he covered it with black paper so the sun couldn't get at it. And then he'd put an object on the photographic plate like a coin or a cross, and then he'd put the uranium compound that was in these rocks on top of it. And then he'd take it out in the sun and let the sun hit the uranium compound, and he thought the sun would energize the uranium compound, like I said before, and the uranium compound would give off some type of rays. And then he'd take it back to his lab, uncover the photographic plate, and he'd see this very light imprint of whatever was laying on the photographic plate. So that's what he was doing. So he wanted to understand phosphorescence or glowing. So that's what he thought would happen. Well, one day he covered the photographic plate with the black paper, put a Maltese cross on the photographic plate. It's like a regular cross. It's not like a cross you see in churches. And then he put the uranium compound rocks on top of it. He was walking outside, but it was cloudy, like our area is all the time. So he put the stuff back in the drawer. The photographic plate with the black paper on it, the Maltese cross, and then the uranium compound rocks. Put it in a drawer, close the drawer. Well, for 3 days, it was cloudy. And on the 4th day, he said, oh, good, finally we have a sunny day. So he took out the photographic plate, the Maltese cross, and the rocks. And for some reason, he goes, let me look at this plate. So he took the rocks off. Then he took the Maltese cross off. He opened up the black paper, and lo and behold, there was the shape of the Maltese cross on the photographic plate. So here you can see the image of the Maltese cross on the lower right-hand side. Pretty cool. It blew him away. So what that told him was that these uranium rocks didn't need sunlight to energize them to shoot out these laser beams. This uranium rock spontaneously gave off these beams or rays, and that's what exposed the photographic film. And that was the start of radioactivity. Even though that word wasn't around yet, that was the start. So everybody was all excited about this find, and there was a young woman from Poland. Her name was Marie Sklodowska, and she was brilliant. And she and Becquerel talked back and forth, and finally Becquerel gave this woman this type of rock that they call pitchblende. And she wanted to see if there was anything in that rock, because she was going to purify it and see if she could break it up into other elements. So she started work on breaking up this rock and into different elements, if there were any in there. And she met Pierre Curie. And Pierre and Marie, they fell in love, and in 6 months they got married, and they started working on this together. Well, she did find something in that pitchblende. And what she found was a new element. Now, but she goes, I'm going to name this new element after my country, my home country. Her home country was Poland, so the name of this new element was PO, and that is polonium. And I'm sorry, polonium has 84 protons, but nobody found protons at that particular time. All right? So she was all excited, but then Marie and Pierre found another element. And this element, wow, it was the hit of all the scientific community. This element that they both found was Ra. This one had 88 protons, and it glowed in the dark. So it radiated light. So since it radiated light, they called it radium. And I gotta tell you, they were the hit of all the parties in Paris, because they'd go to a party and they'd turn out all the gas lights, and Pierre would whip out this test tube out of his coat pocket, and it would glow in the dark. And everybody was amazed. But when he would pass it around, people were noticing that his hand was shaking and his fingers were all dried up, and the skin was peeling off, and also some of his hair was falling out a little bit. And Marie and Pierre were very tired. It didn't take them very much to get very tired. Nobody knew it, but this was the start of radiation sickness. And the word radioactivity, Marie is the one that coined that term. So, after a while, in 1904, I believe, Becquerel, Marie, and Pierre all shared a Nobel Prize. Next, unfortunately, this radiation sickness got a little bit worse and worse and worse. And what we think happened to Pierre is we think he started drinking more and more. And one day, as the tale says, he ran out into the road and he was run over by a horse and carriage and killed. Now, Marie had 2 girls, and one of the girls followed in Marie's footstep, and she also won the Nobel Prize. I mean, they were incredibly intelligent. And Marie eventually died of radiation sickness, and she wrote down every day in a journal what was happening to her. So, that was the start, or the history, of how radioactivity began. Becquerel, Marie, and Pierre Curie were the big players in this. So let's fast forward to 1916 in New Jersey. This is a picture of a bunch of women, about 80 of them, painting dials of watches and alarm clocks with radium to make them glow. Well, you guessed it, all 80 died very painful deaths. Some of the problems they encountered were their jaws were breaking apart, their mouth would not stop bleeding, the teeth crumbled, their spines collapsed, pregnancy complications, unexplained weight loss, extreme exhaustion, and hemorrhaging all over their body. This was because they were shaping the paintbrushes with their lips to make them pointy so they could put little dabs on the numbers on the watches and alarm clocks. These women nowadays are called the radium girls. So after the history of radiation or radioactivity, this is called the Uranium Disintegration series. And here's how this works. If a rock or a substance has any uranium in it at all, it will start to break down. So if you look, it starts at uranium 238 is the atomic mass 92. So it starts at uranium 238, 92. And I don't know if you can see it, but it ends right here. And it ends right where that marker is. And that's lead 82-206. So that's where it ends. It starts with uranium and it ends with lead. Now, you already know 3 ways of natural transmutation. Alpha decay. If you have an alpha decay, the mass goes down 4, the number goes down 2. If you have a beta decay, the mass stays the same and the number goes up 1. If you have positron emission, the mass stays the same and the atomic number goes down 1. So, what's happening here is in order for uranium to break down all the way to lead, it has to go through natural transmutations. So watch, because this is going to be the first question you have to answer from this video. Uranium breaks down to here, which is thorium. So uranium 238 goes to thorium 234. So if you see what happened, uranium to thorium, it went from 238 to 234. The mass goes down 4, and the atomic number went from 92 to 90. So mass down 4, atomic number down 2. That, from uranium to thorium, is an alpha decay. Now, the next thing that happened is thorium went from thorium 234 to Pa 234. So the atomic mass stayed the same. But the atomic number went up 1. So the first transmutation was an alpha decay. The second transmutation was a beta decay. So now what your question is you have to count how many alpha decays and how many beta decays it took to get down to lead 206. All right? Because it stops there at PB 206. So what that means is PB 206 is stable. So it starts out radioactive uranium 238 and it goes all the way down to PB 206. So once again, you have to count the number of alpha decays, count the number of beta decays to get down to lead 206. Everybody got that? Okay. Now, I'm going to show you how long this takes. And this isn't a couple days or a couple years. This takes quite a while to do. All right, so now you can see this is the bottom of the graph. And the last one, like I said, this is lead 82-206. Now, watch what it has to do to get there. Uranium 238 takes a couple million years, and there's an alpha, so it spits out an alpha to turn into thorium. Thorium only takes 25 days spitting out betas and gammas to get the protactinium. Then protactinium to uranium takes 7 hours, gives off beta and gamma. Then uranium 234 takes almost a million years by spitting out alpha particles to get back to thorium. That's how it works all the way down. And the final product, after, you ready for this? After about 4.5 billion years, is stable lead. It goes a stable isotope, Pb206. So that is how the uranium disintegration series works. And once again, you have to email me how many alpha decays there are and how many beta decays there are to get to the stable isotope of Pb206. So what we've gone over so far, the history with Becquerel, Marie, and Pierre Curie. We've gone over the uranium disintegration series. Now, on your packet, this packet, it says nuclear chemistry. You have the uranium disintegration series right here. Everything that I showed you on the video is right here. So that's the uranium disintegration series. The next thing we're going to talk about is the artificial transmutation. You already know that natural transmutation, you don't need anything for it to start. It does it by itself, alpha decay, beta decay, positron emission. But for artificial transmutation, you have to hit a stable isotope with something, like an alpha particle, a beta particle, a proton, a neutron, something like that you have to hit it with. Okay? So we are going to do some notes on artificial transmutation. So when a stable isotope, like aluminum, a normal isotope of aluminum is not radioactive. So when a stable isotope So what I have here is when a stable isotope, not radioactive, is bombarded by a subatomic particle, so I just gave a list of the particles that could hit the stable isotope. Protons, neutrons, electrons, and alpha particles. Okay? So when a stable isotope, not radioactive, is bombarded by a subatomic particle like these, so now, when a stable isotope, not radioactive, is bombarded by a subatomic particles like protons, neutrons, electrons, and alpha particles, the stable isotope, the nucleus of the stable isotope, becomes unstable. And then it starts spitting out stuff. What stuff does it spit out? Probably protons and neutrons. Okay? And that, if it spits out a proton, what that means is that stable isotope is not stable anymore. It's a radioisotope, which means it's radioactive. All right? Now, let's put down number 2. Don't forget, natural transmutation. Again, alpha decay, beta decay, positron emission. You only have one reactant. That reactant does it by itself. For artificial, guess what? You need a stable isotope and something to hit it. So artificial, you need 2 reactants. You definitely need 2 reactants. One to hit it and one that's stable. Okay, now let's do one. Let's say we have very stable aluminum. And aluminum is 2713. And this isotope of aluminum is totally stable. Now, let's say we hit it with an alpha particle. Now, once that hits it with an alpha particle, that alpha particle smashes into the nucleus. And what happens is this. Let's just say a proton pops out. Watch how easy this is. Remember, whatever you have on this side for atomic mass and atomic number, you have to have the same amount on the other side. So, I have 27, 28, 29, 30. I have 31 mass there. I've got 1 there, so the mass of the new radioisotope has to be 30. I've got 13, 14, 15 atomic number. There's 1 there, so I have to have 14 there. And 14 is this. So let's look again. 27 and 4 are 31. 1 and 30 are 31. 15 total atomic number, 15 total atomic number. But that silicone is not just normal isotope of silicone. That silicone was formed by artificial transmutation, which means that silicone, that one right there, that's radioactive. So the big deal about artificial transmutation, you have to have two reactants, and then you are going to get a radioisotope at the very end. Same masses, same numbers. Okay, let's do another one. This time, a stable isotope of calcium is hit by a neutron. And what happens is, once that neutron hits the nucleus, this happens. An alpha particle gets spit out. And if an alpha particle gets spit out, well, then we got to see what the radioisotope is. So, 40 and 1, that's 41 minus 4. All right? So, we have 37, and we have 20 and 0. We have 2 there, so this has to be 18. And 18 happens to be argon. So, we have our two reactants, because it's artificial transmutation. Alpha particle gets spit out. When the neutron smashes into the nucleus of calcium, alpha particle gets spit out, and that produces argon. But this argon, like I said, that argon is radioactive. Now, knowing that, here's the other part of your homework. So remember, the first part, you have to tell me how many alpha decays and beta decays there are in uranium disintegration series. And the next part is this, problems. Right underneath the uranium disintegration series, you have 5 problems to do. And some of them are artificial, and some of them are natural transmutation. Okay, so you just fill in. You can write if it's artificial or natural, and then you can write down what the question actually wants. Okay? All right, that's good.